So I've said it before many times to engineers, and I'll say it here for you, but I do believe that everyone should get into the habit of hardening your system for EMI up front. And that is basically the best thing you can do. For EMI coating solutions, there are several categories to consider for your design. The electrical properties, such as EMI shielding or conductivity, are always a primary concern and can impact overall cost. The polymer-based material should be chosen based on the type of substrate, the operating temperature, chemical resistance, and other requirements for coatings can include UV protection, impact or shock loading, and wear limitations. These issues can come back fierce and can really add complexity to fixing your design when and if it fails EMI and you didn't consider these things up front.
A few of the mechanical considerations to consider when planning conductive coatings are adhesion strength, coating thickness, and flexibility. Adhesion strength is important to consider because not all polymer binder systems will adhere well to various substrates. Oftentimes, surfaces must be prepared with primers, adhesion promoters, or physical and chemical etching that we will discuss in more detail later in the webinar.
Yeah, and Ben, I'd like to add a word of caution on that note. When you consider using a chemically resistant plastic, that means that the plastic will resist the chemical coating. So I've seen these parts get sprayed and then literally the paint is dripping off and not adhering. So on that, coating thickness is referred to as a dry film thickness because the paint thickness is measured once all of the solvents have been evaporated off during the curing process. Coating thickness is impacted by particle size as well as the accuracy of the painting process, and in addition to the surface protection qualities of the recommended thickness of the paint, the coating thickness also has an impact on the electrical properties and really should be measured and validated to ensure proper performance.
And finally, different binder systems will have varying levels of flexibility. Some applications will have unique and complex geometries that will require less viscous paint to fill in tight angles and small crevices. Greater coating flexibility is a benefit on substrates that are subject to thermal expansion and contraction, as well as intended or unintended flexing or bending.
So because we're talking about conductive paints, we need to know about the electrical properties. Lower conductivity filler systems are often associated with lower levels of shielding and more cost-effective solutions if the shielding requirements are moderate. But as with other solutions, the overall conductivity is driven by the individual particle conductivity as well as the level of fill in the paint. So coatings need that even distribution of the fillers throughout the part to make sure the entire surface has the ideal properties.
On a very important note is that EMI shielding is not always directly correlated with particle conductivity. Let me emphasize this. High conductivity particles will provide good EMI shielding, but low conductivity particles can also provide very good EMI shielding because of factors such as particle shape, particle size, and paramagnetic or ferromagnetic properties. These properties will actually impact the shielding at lower ends of the frequency spectrum, specifically in the magnetic field range.
And finally, galvanic corrosion applies when the material with the different electrical potentials come in contact with each other and in the presence of an electrolyte, such as salt fog or atmospheric moisture. When conductive coatings that have particles such as silver, nickel, and copper, these are bound to be voltage differences within the aluminum, the titanium, and the steel substrates. So fortunately, there are steps we can take to reduce the reactivity of these conductive parts.
Finally, we wanted to talk about environmental considerations. The environment in which the coating is operating will have an impact on lifespan and performance. For example, all paints have an operating temperature range that is mostly driven by the temperature limits of the polymer binder. Epoxies will have a higher maximum operating temperature than acrylics, and many polyurethanes will actually be able to operate at lower limits than many others.
Likewise, different polymer systems will have different resistances to harsh chemicals and fluid washdowns. So most coatings will hold up well to harsh chemicals, but are often paired with a non-conductive top coat to protect them from varying environmental conditions. So corrosion resistance is a concern when coatings are exposed directly to the salt fog or corrosion-inducing environments.
We wanted to provide you with a basic summary of coating polymer properties and how they compare based on some mechanical and environmental factors. So for example, as you can see, acrylics tend to perform at a lower level in most of these metrics compared to other polymer systems. This doesn't necessarily mean that they cannot meet program requirements, but we often see acrylics used in applications that may be protected from the environment or in places where temperatures are more controlled. Likewise, epoxies have fantastic strength and temperature resistant properties, but are not recommended on substrates that may flex or bend or undergo vibration because of their brittleness. For such an application, polyester-based paints may be the best solution.